started. Okay. Number one, I'd like you to sketch the solution region of y is greater than 0 and y is less than or equal to 10e to the 0.2047x. And then after you sketch that solution region, tell me whether or not it's bound or unbound. And then item number 2, we'll talk about this week's schedule. I have a bit of a survey for y'all to fill out that I'll post in a second. Also, I think my autofocus is 1 step off. Give me a second. Yeah, it was 1 step off. And then today we'll have notes on the last section that we're going to cover before the mid-chapter quiz. Go to Google Classroom right now while y'all are working on that warm-up and fill out the survey. Survey is 1 question. Do you want the mid-chapter quiz on Wednesday or Thursday? Mid-chapter quiz on Wednesday. We finish up a little bit early and all head out to break a little bit early. Mid-chapter quiz on Thursday. You have 1 extra night to study these 4 topics that we've covered while we've been at home before we have that quiz. It's up to you. I'm going to go with whatever the majority says. And like I said, that survey is up on Google Classroom.
Yeah, Mr. Robinson.
Stop taking input on it in about 10 minutes. Yes?
If we're taking a new lesson today, how are we going to do a mid-chapter quiz on Wednesday?
Because tomorrow would be the workshop for that section and the review, and then it would be on Wednesday.
Oh, so like two lesson workshops in a day.
I guess, yeah. That's why I'm making it up to you in case you want that extra day to study, or if you think this stuff is easy and you just want to get it over with and out, you know? It's your call. Oh, no, I'm sorry. I mean, it's your collective call. But yeah, take that survey real quick. Oh, wow, God, that's so fast when we're all already on our computers. Yeah, like I said, I'll stop taking those at 8:30 so the people who are absent, you know, they just jump into vote. Okay, so let's go ahead and get started today on this warm-up. Number 1, we would like to sketch the solution region of y is greater than 0 and y is less than or equal to 10e to the 0.2047x. I'm going to go ahead and start this off by setting up my axes. And I'll just be using a regular old linear scale. This is one of those graphs where the scale actually doesn't matter that much, mostly because the general shape of this, at least as well as you can capture on a piece of paper with a pen or pencil, is going to look more or less the same. The only thing that you could do that might be useful is you could label the y-intercept for that exponential graph. But nonetheless, the first equation in our solution, y is greater than or equal to 0. What is that? What does that condition look like when we sketch it and graph it?
It's a line. It's just a flat line on the x-axis.
It is the x-axis, but which way do we shade?
Oh,
Upward.
Yeah, so for that one, we would shade upward. So all that this is saying, y is greater than 0, just means above the x-axis. For the second one, that's the actual interesting one. So that's an exponential growth graph. And what do I get for that function when I plug in 0? What is its y-intercept? What happens when you plug in 0? What do you get?
10.
10. We get e to the 0. Anything raised to the 0 is 1. 10 times 1 is 10. So one thing we could label on here for this y-intercept is the fact that that y value is 10, x-axis, y-axis. And then from there, we have some kind of exponential growth. Put an arrow on it. And y is less than 10e to the 0.2047x. So if we plug in our origin, right, 0, 0 is a test point, does that come back true or false? Is 0 less than or equal to 10?
True.
That's true. So that means for this guy, we would shade down.
Okay, so Mr. Robinson, this is an unbound graph?
Yeah, this is unbound because it's bound above and below. We have an upper limit, we have a lower limit, but there is no limitation left or right. So because this goes off to the right forever as this exponential goes up forever, then yeah, this one is unbound. Is that okay? Any questions there?
Ms. Robinson,
Mm-hmm.
do we have to, like, for the exponential graph, should we just draw to our best, like, estimation, or should we get the exactly what it is? Like,
You can't. You couldn't, no matter how hard you tried. You cannot capture what an exponential graph does or how it behaves by hand, not well at least. Not unless it's something designed to be capturable. Like if it's base 10 with nothing else going on, then you could easily make a perfect graph because it'll go from 10 to 100 to 1,000 to 10,000, but if the base is e, no matter what, you're just going to end up sketching that generalized shape, but you could never capture precise points. Also, on the topic of this week's schedule, I have enough votes in now to call it decisive. With 72%, we're going to be taking the mid-chapter quiz on Thursday. So we'll have the next 2 days after I'm done with the notes today to work and ask questions. And then Thursday during first period regular class time, we'll have a 1-hour mid-chapter quiz. Are there any questions on that stuff?
Yeah, Mr. Robinson, how long is the quiz? How many questions?
Full class length
usual?
period. Yeah,
Okay.
as usual. Yeah, like literally as usual. Like it's the same types of quizzes that I give y'all to take in class, but you'll be taking it in the comfort of your own home.
Okay.
And make sure that you're on time for it, because the thing that I've been doing so far with assessments while we're doing take it home is you have 10 minutes to upload it, but after that 10-minute window to upload it, you lose 1 point per minute. So, you know, don't start it late, don't turn it in late. Be sure to finish it up early and get it in on time. Anyway, anybody want to take a wild guess what the context is for question 1? What my deal is there? Come on.
System of equations with exponentials.
Yeah, and the whole deal with exponentials is simply the fact that I'm convinced nobody actually really learns exponentials the first time they use it. Most people in pre-cal do a bad job of understanding what exponentials and logarithms are actually talking about. And then later on in your life, you'll end up having to use those same functions in calculus, where you get a much better chance to grasp at what exponentials are attempting to describe. Like a lot of people, the problem that I used to have when I was your age was I would like mix up the way that an exponential grows versus the way that a quadratic grows, because in your head, you know, they're both just curves instead of lines, but the rate at which an exponential grows drastically outpaces a quadratic in a way that like I just don't think the average human brain can actually grapple with. So here's my deal with talking about it today. Let me show y'all what this system of equations looks like in Desmos, just to start this off. So I'm sharing the window with you, yeah?
Right.
Yeah. So this is y is greater than 0. That's the red line. That's boring. That just makes it so that we're above the x-axis. And then I have y is oh, I'm sorry. It should be less than or equal to if I'm going to match the warm-up. Less than or equal to 10e to the ax. And then I have a as a constant, and this slider is set somewhere between 0 and 1 in very small steps so that I can get close to what the warm-up was. This is actually a little bit higher, but you know, it's a pretty finicky slider. Let me get it a little lower to 0. Sure, that's probably closest. Anyway, here's the deal. In terms of exponential growth, 0.2047 is actually the exponential growth constant for infections in the United States right now in terms of coronavirus. Now that's a national average. It's not growing equally fast in all areas. It's growing a lot faster in Louisiana, Florida, and New York than it is in other states. California's growth rate constant is a little bit lower. But when we look at what changes this makes for the exponential growth graph, like just small changes in this constant, right? Here's what that looks like in terms of exponential growth. A slight decrease in constant makes it so that the graph grows slower. It doesn't increase as much until larger x's. And the higher this growth constant is, the quicker the number increases. But you can see here that even though there should be a big jump between 0.5 and 0.9, the perceptible difference in terms of what the outcome is for the trajectory of this graph is really hard to tell. Now, one way to tell this difference is to zoom way out and try and look at a larger space. So let me take a little bit to zone out. I'm also going to destroy this thing because this is making it load slower. It'll load a little bit quicker if it's only one graph, but it still won't load that fast. So now if I zoom out to a couple hundred times where I was before, now we can start to see how the changing of this constant will affect the growth rate and how decreasing this constant will also affect the growth rate pretty drastically as we bring it down. Are there any questions there on that stuff?
No.
What's the point of staying at home?
To make it less drastic, I guess, to give it more time. Because either way, I mean, exponentials go on forever. So
Yeah, but infections don't, because that's the breakdown
okay.
between math and actual application. Eventually you run out of people to infect. So at
Right.
some point, instead of this being exponential growth, it switches to a different kind of graph that we like touched on for literally 10 minutes during the exponential and logarithm sections called logistics. And actually today, the video that I'm referencing with my little like warm-up question today discusses how you can try to predict that turning point. My point with this first part is just the notion that like a linear graphing scale, when you're talking about exponentials, is basically worthless, right? And what I mean by linear scale is that the gap between these lines remains exactly the same. These are all differing by 100. A radically more useful scale for talking about exponentials is called a logarithmic scale, which is what you see in this window right here. This is one of my favorite graphical resources on the COVID virus right now. What do you all notice about the X and the Y axes here?
It
Look like
goes up by
tens.
multiples of 10.
Yeah.
Yep. So lines that are equally spaced, instead of going up by the same amount every time, these are increasing by 10 each time. So this is 100, 1,000, 10,000, 100,000, 1 million. And then in the other direction, same thing. Instead of increasing linearly, we are increasing by factors of 10. When you take an exponential, e, and you graph it on a logarithmic scale, right? Like when you do the math, what happens when you take the log of an exponential or the exponential of a log?
Cancel or no,
Yeah, they cancel, right? So if I had y is equal to e to the x and I hit that with a log, what do you end up with?
X, just
yeah,
X, right?
yeah,
You end up with just x, just a perfectly linear x. Now, the reason why logarithmic scales even exist in mathematics is for the straightforward point that if you take an exponential function and you graph that onto a logarithmic scale, it does what we call linearizing the data, which will make it so that on this particular scale, y is equal to e to the x would just graph a perfectly straight line. It makes it so that instead of exponentials just growing up infinitely high, almost in an imperceptible way, this forces the exponential graph to appear linear, which makes it a lot easier to discern small changes and details within that linear graph. And also, just so y'all know, I'll be posting these links to Google Classroom afterwards. All of the data that's in that logarithmic graph that I was showing y'all is from this resource, Johns Hopkins University, which this is currently the best, almost only authoritative data on the current outbreak rates in the world. On the left here, you can see, wait, have I shown y'all this page before? Yeah, right?
No, we've never seen.
yeah.
Oh, word, I guess I did this with AP Physics last week. Anyway, I'll post this link to Google Classroom in case you want to look around. It's got a global map of current infections. Size of the dot is the number of infections in that region. Left-hand side is the current ranking of infections by country. All of that good stuff. You can zoom out, zoom in, do whatever. And for whatever country you select, on the bottom right here, it'll show you the graph over time in case you want to do any of this mathematical analysis on your own. I'm mostly just excited for this. I mean, don't get me wrong, a lot of people are going to die, but I'm also mostly excited for this stuff because now when I teach exponentials and logarithms for the rest of my life, I will never have to answer the question ever again, when will this information be useful? But nonetheless, here on the left, here's the United States infection rate over time. Again, it's another exponential where you can't, your brain just can't really wrap around what's going on. Here's Italy, another exponential where your brain really can't wrap around what's going on. And then here's China, which is not an exponential. This is a logistic curve where we have exponential growth at the beginning and then some kind of turning point, and then it flattens out at the top and becomes logarithmic in its growth rate. And again, your brain still not good at grasping this exponential growth part. What's the question? Somebody was trying to ask a question out there, but I just railroaded through. What was the question?
Yeah. Yeah. How did the U.S. cases surpass Italy and China within a few weeks?
Because we started testing more.
I mean, tests, but
I mean, we started
didn't
testing.
know what the number was a few weeks ago. We just started testing.
We started testing at all, which will always increase the number artificially, right? So that's the same with autism rates is the big one of people being like, oh, there's a autism no, it's just that a bunch of diseases that were not considered autism in the early 90s, things like Asperger's, were put on that scale, and now addressing all of them increases the number. There's also just the fact that response time to the outbreak, we knew that the disease was spreading from other parts of the world to the United States for about 2 weeks before we did anything about it, which gave a lot of travel time for the baseline in our country to be some large number instead of it being 10 or 15 or whatever.
Yeah.
And Mr. Robinson,
Yes.
how do you know any of this is
Crazy.
true though? What makes any of this true?
Oh, I don't
Like,
know. That's the wildest question that I just like can't, like, on its face, that question being asked drives me insane. I don't know, because it's science and I'm a scientist. Like,
No, I mean,
what
how do
else
you
do
know
you
these
have to go
numbers?
on?
I mean, how do you know these numbers are true? What makes these numbers reliable?
The fact that they're being reported by hospitals.
I don't know, but how do you know those numbers being reported are true? What if it's a
How do you
lie?
know that anything is true? Like, how do you know that your birthday was true? Like, do you remember being born?
No,
Because
what people
that's
do
just on
remember
a
being
piece of
born.
paper that came from a hospital, right? Like, I don't know that that's true. Questions of how do we know that things are true are deeper philosophical questions that have to be addressed by a different instructor other than myself. And I usually find questions like that, especially for discussions like these, tend to be unnecessarily distracting. Nonetheless, exercises in mathematics. That data, that exponential growth on regular linear scales, it's really hard to parse information from it, which is why I greatly prefer looking at exponential data on a logarithmic scale. Back in the day, before we had powerful computers to do this analysis for us in whatever scale we wanted, literally the way that people figured out the properties of exponentials was by drawing them on logarithmic graphs and then measuring the slope, because the slope of an exponential graph on this scale will give you back the growth constant. And here's what the data looks like playing out since January for the infection and the outbreak in various countries. Where it ends with the current date, and this will be updated with numeric data as, you know, things progress. What do y'all notice about the graph here?
China goes down pretty hard, and then USA.
US is just keep going exponentially.
Yeah.
So
It's slowing down at its source and it's speeding up everywhere else.
I think that might just be an artifact of like the fact that I'm capturing a screen or whatever. It's supposed to increase with constant speed, but keep in mind that this is not infections versus time. This x-axis ain't time. It's
Yeah.
the total number of cases that are being experienced by the country versus the new number of confirmed cases within that same week. This is a much better way to try and capture this data, right, to analyze it, than graphing it versus time is. Because this basically makes it fair weighting in terms of like the population of the country. Like, it's hard to compare different countries with very different populations. But what do y'all notice about things about this trend when it's on this logarithmic scale?
It's linear.
It's linear, but it's more than that. What about the things that don't fall on the trend?
They just drop, I guess.
And what does that mean? Read the X and Y axes. What's true about South Korea, China, Japan in this state, Italy in this state?
The new confirmed cases drop.
Yeah, that's what I'm actually looking for. So when it comes to comparison of exponential graphs, it's really hard to tell the difference between one exponential graph and another. Like, let me remind y'all that when it came to that little equation from the warm-up, this guy, you can flex this constant back and forth, but what it's going to do to your graph is imperceptible. It's really hard to tell the fine differences unless you take a large look. And you definitely can't draw that difference by hand on a piece of paper, right? However, when you look at the linearized version of this data, small changes in the infection rate become extremely easy to tell because they cause deviation from this main line. Like I said, I'm going to post both of those resources on Classroom. And I don't know, we could question whether or not anything is real, I suppose. But nonetheless, I'll make that resource available for you in case you're interested. Now I'm going to switch gears. Today we're talking about our final section of the 4 that'll be on the mid-chapter quiz, and tomorrow we'll get a chance to work on it. This is a section which is theoretically a thing that you've already done, but whether or not that's true usually surprises me. Today we'll be talking about 9.4. Today we're discussing partial fraction decomposition. Anyway, partial fraction decomposition is and I don't really get why it's in this section. I actually think this would be better off right after rational functions, because this is actually us talking about rational functions. It's just that we're going to use a little bit of system of equations stuff in order to get the answers to these problems. But what partial fraction decomposition is it is simply a technique that allows us to rewrite any rational function that can be factored as a sum of much simpler terms. Now, who remembers what a rational function is?
Is it like when x has a square root?
Not quite.
Like
There
the
is a
whole
relationship
thing.
between the word rational and taking a square root of a function, but a rational function itself is actually different. For those of y'all who don't remember, a rational function is a quotient of two polynomials, one polynomial divided by another. And those are the questions where we would have to take the denominator, set it equal to 0 in order to find asymptotes. And there were a bunch of different asymptote rules for how the numerator and the denominator of the rational function interact with one another. In this section, we won't be talking about the asymptotes of rational functions. Instead, what we're going to be doing is a little bit more brute force calculation. Please consider the following example. Let's say that I would like to add the following two quotients. I want 3 divided by x plus 2 plus 5 divided by x minus 1. What's the rule about adding fractions? What would I have to do here?
Common denominators.
Yeah, we need a common denominator. So what I would have to do is I would have to multiply this first term by x minus 1 over x minus 1. And I would have to multiply the second term by x plus 2 over x plus 2. Because each one of those fractions is secretly equal to 1, so multiplying the original term by that won't change its value. It's just going to make it so that they are combinable. And so here I'm going to get 3x minus 3 divided by x minus 1 times x plus 2 plus 5x plus 10 divided by x minus 1 times x plus 2. And now that the denominators are exactly the same, I can add straight across the top, which is going to give me 8x minus 7 divided by x minus 1 times x plus 2. Now, I guess that's neat. That's just a little bit of algebra. I'm sorry, it's not even that. It's a little bit of arithmetic. I'm sorry, this should be plus 7, huh? But what partial fraction decomposition is going to allow us to do is it's going to allow us to go from here back to here. So how is it that we could take this this rational function, and rewrite it as this, a sum of simpler terms? So instead of this being the start and this being the end, Partial fraction decomposition is a technique where we take this as our starting term, and then this is our ending term. And now the weird part is, Will, why would you want to do this? What's the name of this class?
Precalculus.
Yeah, which we always lose sight of because it just feels like what we're doing is algebra 3. The point of this will not be immediately clear to y'all, but next year when you take calculus, you are going to find that in terms of doing calculus type operations, and the two main calculus operations are the taking of a derivative and the taking of an integral. This is a nightmare object to deal with if you are doing those things. If you are trying to do a calculus to this, this is garbage. If you do a calculus to this, this is trivially easy. It's one step of math. This is one of those things where this is actually meant as a lesson to get you ready for what you'll be doing next year, be it in a high school or a college. So let me talk a little bit about the rules of how we set this up, and then I think it'll show y'all why this is in this chapter at all. So the general approach is we are going to take the rational function and we are going to factor the denominator. After you take the denominator, we are then going to write a sum of terms with unsolved coefficients in the numerator.
What do you mean by unsolved coefficients?
I mean that they are coefficients that we haven't solved for yet. You'll see, it'll make more sense. I mean, like most instruction sets, I'm just going to list this out now and then I'll model it for you. I just want to make sure that we have this written down first. And then after we write a sum of terms with unsolved coefficients in their numerators, we are then going to multiply out all denominators. The act of doing this will create a set of linear systems which we can solve. This will create a system of equations. And then after we have that system of equations, then we can solve for our unsolved coefficients. So while this is fresh, while we have this down, we're going to go ahead and we are going to work through that example that we did in the previous line, except we're going to work it backwards. And then after that, I have an important follow-up about this rule right here. Write a sum of terms with unsolved coefficients in the numerator, because this is more complicated than it appears. It's just that this first example that I set up is designed so that it's straightforward. Sorry, I'll come back to that after we do this example. So hey, for example, let's say that I have the following rational function, 8x plus 7, divided by x squared plus x minus 2. What do y'all notice about this particular rational function?
The denominator could be factored.
Yeah, factorable.
First of all.
Sure. So this is actually equal to 8x plus 7. And then what does that denominator factor into?
Take out x, so
X minus 1.
X plus
Like,
1.
no,
x of
X
x,
plus 1.
x of 1
X minus 1, X plus
1.
2.
Yeah, x minus 1 and x plus 2. So again, what do y'all notice about this rational function that I chose?
It's the same one as the first line, the top one we did.
Right, this is the same thing as the previous example, so that we already know what the answers should be. We know that the answers, when we're done with this technique, the answers should be 3 and 5, right? I just wanted to start with an example where we already know what the answer is and we know why it is the answer, right? So that it's easy to model this technique. So here's how we do partial fraction decomposition, which is to say, I want to take this total fraction and I want to decompose it into partial fractions, right? I'm going to say that this is equal to a sum of terms where each piece in the denominator is one of the terms that I have just factored out. So since that denominator factors into x minus 1 and x plus 2 perfectly, I know that I can rewrite this thing as a sum of 2 fractions. Now, what I don't know is what those numerators would have to be so that it matches here, which is why I'm going to set them to be unsolved coefficients. Just like all algebra, if there's some number that I don't know what it is, right, I'm going to set a letter to it with the expectation that if I do the right steps of algebra, I'll get those letters back. So I'm going to say that this is A and this is B. So that's step 1 of that little technique that I gave y'all. What is the next step of the technique?
Multiply.
I'm now going to multiply out all denominators. So the total denominator that we have is the combination of x minus 1 and x plus 2. So I'm going to multiply this thing's entire world by that, x minus 1 and x plus 2. So here, the effect of this multiplication is obvious. It destroys out all denominators. So this gives me 8x plus 7 is equal to, what happens when I multiply this into the term with a?
Ax minus
Doesn't
8.
it just become a?
No.
Nope.
It becomes x plus 2a?
Correct. The x minus 1 gets destroyed by this x minus 1, and what survives is the x plus 2.
Oh, right, and then x plus 2.
Yeah.
So this becomes ax plus 2. And then for the b term, I take this and I multiply it into b. The x plus 2 destroys the x plus 2, and what survives is x minus 1. So this becomes plus b quantity x minus 1. Okay. So now what I'm going to do is I'm going to go ahead and I'm going to expand the right-hand side. So this is going to give me 8x plus 7 is equal to ax plus 2a plus bx minus b. And now I'm going to combine like terms. So this gives me 8x plus 7 is equal to a plus b times x. You'll notice I have an ax and I have a bx. I can combine those like terms and factor out x. And then I also have plus 2a minus b. So here's the deal. I know that a and b have to be constants. That's just like one of the rules of this technique. And since none of them can be x, a can't be a multiple of x, b can't be a multiple of x, there is nothing about this constant part that can contribute to the 8x on the left-hand side. So what we're going to do here is a little mathematical trick called correspondence, where I know that this this constant has to correspond to this constant because there are no other constants. These two here have to be equal. And in the same way, this part with the x, a plus b times x, must correspond to this 8 times x. And so I know that this part, the a plus b times x, must go hand in hand with the 8x. And this is what gives us that third line of our rule set, solve for the unsolved coefficients. Because of correspondence, here is the system of two equations which I can now write. I now know that 2a minus b, I'm sorry, I don't like the way that's written. They're a little bit too close for comfort. Just like all of the people outside running. Man, I don't want to have to edit this. I have a story to tell about a bad interaction I had yesterday while I was out running. I went out for a half marathon, like a long distance run, And this dude running intervals kept getting way too close to me. That is definitely another American who has no concept of how far 2 meters is. Anyway, 2a minus b must be equal to 7. That's one of the things that correspondence of these two functions tells us. Here's the other thing that the correspondence of these two functions tells us. 8x is equal to a plus b times x. Now this is problematic because I have 3 variables and 2 equations, right? I have a, b, and x, but I only have 2 relationships. However, luckily there's a way around that problem in this case. What is the way around? What's very clever about this?
You can substitute maybe?
Correspondence.
I already used correspondence to write these 2 equations, and
Oh, you're saying-
substitution
oh,
does
okay.
not get us over the hump of I have 3 variables and 2 equations.
Oh, right.
Here's what does get us over the hump.
Oh, I
I
see.
don't need x. The point of this technique is not to solve for x. Our answer is not going to be numbers. Our answer is going to be an equation.
Divide by x.
So on the right-hand side here, I can divide by x, and now I know that 8 is equal to a plus b. And so we give up the ability to get x, but hey, now I have 2 equations, 2 variables, and now I can definitely solve for b. And notice, I'm sorry, a and b. And notice here, I think elimination will work pretty well, right? What 2 variables will eliminate if I add these equations together?
B.
Yeah, this is set up so that b eliminates right off the bat. So I'm going to take these 2 equations and I'm going to add them up. So I get 2a minus b is equal to 7. And I get that a plus b is equal to 8. 2 equations, 2 variables. I can take these guys and I can add them. B and b eliminate. I get that 3a is equal to 15. So therefore a is equal to 5. And once I have that a is equal to 5, I can take this and I can plug it into either of these equations to solve for b. So that tells me that 5 plus b is equal to 8. Subtract 5 from each side. B is equal to 3. And here's an important note for these partial fraction decomposition questions. The answer is not the constants a and b. The answer is the function that you get when you take and you feed them back in. So in my original setup, I said that this guy would be equal to a divided by x minus 1 plus b divided by x plus 2. And that's what we just solved for, a and b. And so I know that that original fraction decomposes into 5 divided by x minus 1 and 3 divided by x plus 2. Are there any questions about partial fraction decomposition, this very basic version of this technique?
Mr. Robinson?
Yep.
So in the homework, we solve it in terms of a and b.
It just depends on the needs of the problem.
Okay.
I mean, the way that math works is it doesn't matter which variables you choose, right? In the end, the answers are going to be the same as long as the technique that you do is correct. So instead of calling these A and B, I could have called them C and D. I could have called them
No, I know.
COVID
I just
and
meant
SARS.
I just meant like in terms of 2 other variables, like adding 2 other adding A and B or C and D, whatever.
I don't understand the question.
Okay, never mind. I got it. I'm good.
Okay, sorry. Is there another question out there?
Yeah,
Yeah,
Mr. Robinson.
Yes?
Does the denominator always have to factor for these types of problems?
Yeah, if the denominator doesn't factor, then there's no problem to do at all. Yeah, this only works if the denominator is factorizable into linear terms that have constants.
All right, thank you.
Yeah, it's a good question. Are there any other questions on this initial example here?
Mr. Rob, if like for instance like this one, like 5 x minus 1 and 3x plus 2, what if like the numerators here like it was 5x or like 3 plus 2x, like something like that?
It's outside the scope of this class. That can't happen.
Okay.
if that were to happen, then your numerator would have been more complex to begin with. Your numerator would have been something of the form something x squared. And if that's the case, then you would simplify terms in the numerator with terms in the denominator before you started.
Okay.
So if the numerator was more complex, it would cancel out with terms in the denominator.
Okay.
All good questions. And now let me go ahead and get back to that little red asterisk that I made on the notes when we were talking about this method right here. So write a sum of terms with unsolved coefficients in the numerator. This is where I need to make the important caveat that it's not always just going to be A, and it's not always just going to be B. It could be something a little bit more complicated. Let me show you what to look out for. Here are additional rules about unsolved coefficients. So, depending on how complicated your function is, the unsolved coefficients that you set up might also end up being themselves fairly complicated. And so here's what we have in our denominator. And then what we would have to look for in our numerator are unsolved coefficients. So this previous one was the most straightforward version of this. And just in case you're trying to make your notebook pretty, what I'm about to give y'all is 4 lines, and then we'll be done for today. In our denominator terms, we had simple linear factors, ax plus b. In those cases, that's where it's appropriate to just set a single letter to your numerator. So our numerator in this case was just a divided by ax plus b. And I had one term of these for each one of these terms here, right? So I had 2 linear terms. And so I had 2 terms in my numerator. Here are the cases where your unsolved coefficients might get uglier. Let's say that we have a repeated root. Sum ax plus b to the k. This could be ax, x minus 2 quantity squared, x plus 1 quantity cubed. What do you do when you have repeated roots? What you are going to have to do in this case is that your numerator terms will have to include one unsolved coefficient for every single possible power of the denominator. So here where this denominator is k, you would need 1 a divided by ax plus b. You would need b divided by ax plus b quantity squared. You would need c divided by ax plus b quantity cubed, all the way down until your final constant. And again, we don't know what this is, so this is just for example. K divided by ax plus b to the lowercase k. So if you have some higher power, you need 1 letter for every power between 1 and whatever that power is. Next rule. Let's say that we have something which itself is not factorizable, right? We have some kind of quadratic which doesn't break down, but we still need to break it up into partial fractions. So let's say our denominator is ax squared plus bx plus c. The terms in your numerators need to be 1 degree lower than the term in your denominator. So here, where our denominator is linear, our numerator is just a constant. This is what we consider to be degree 1, and a constant is degree 0. What's the degree here?
2.
The degree is 2, subtract 1. That means our numerator term would have to be linear. So if you have something like this in your factorized set, this would have to give us ax plus b divided by ax squared plus bx plus c. So if you have a quadratic term which doesn't factor, the numerator term that goes up above it has to be linear. And this could be for any possible power. If you had a denominator term that was x cubed and it didn't factor, you would need your numerator term to be ax squared plus bx plus c. And then the final notice that I'll give y'all about this technique is that unsolved coefficients can be 0, so don't be weirded out by that. Every now and then you'll set up some sort of set of unsolved coefficients and you'll try to solve for them, and the answer might be 0 for one of them. That's fine. It just means that it's not a contributing term to your overall set. I'll post the homework, and then tomorrow for the warm-up we'll have 2 hard questions of this type. Feel free to get started, but like I said, we have tomorrow for workshop on the section. We have Wednesday for review workshop, and I figure that'll be a second shot to get your questions in for this chapter. But other than that, y'all have a nice day, and I'll see y'all tomorrow morning.
Thank you, Mr.
Mr. Robinson.
Peace.